Hi there, I'm Robert Bingham from the School of Geosciences in the University of Aberdeen, and in this short video I'll be explaining the recently reported theory from myself and my colleagues at British Antarctic Survey that the current pattern of ice thinning we observe today in West Antarctica is inherently influenced by geological processes that have occurred over millions of years. Our video begins by showing the current situation across Antarctica. At the moment, what you're seeing is ice over the Antarctic continent in grey, surrounded by the sea in blue, and we're zooming in to West Antarctica. What's now fading in is a representation of the current pattern of ice thinning across the ice sheet as measured by satellites, and the areas to focus on are those coloured red, where the most thinning is taking place. You can see that these are generally around the coastline. Now, one of these places is Ferrigno ice stream, which I've just highlighted there with a black polygon. And a big question that scientists are trying to answer is why some parts of the ice sheet, like Ferrigno ice stream, are so vulnerable to ice thinning today. To try to understand this, we have to consider how the continental geology has evolved from a time before the ice sheet ever grew. Where the story begins is millions of years before today, way before there was ever any ice cover over the continent, and the Earth in general was warmer than it is now. So what you're looking at on screen now is the rock surface of the Antarctic continent over 30 million years ago, essentially an intact high plateau shown mostly in red. And I've left on there today's location of Ferrigno ice stream for orientation. From that time until today, over millions of years, this continental crust has been subjected to powerful geological forces, and the result of this has been that beneath West Antarctica, which we're zooming into, this paleo surface has been dissected by rifting processes. That's represented on the screen there by a simplified transition to the current subglacial topography, with high points remaining in red and low points in green and blue. At the same time as this geological evolution has taken place, the continent has also been glaciated and deglaciated multiple times, with ice initially growing and extending out to the continental edge as shown on screen now. Ice flow out from the interior of the ice sheet has been particularly intensified along the lines of least resistance, and so, where there is already a line of weakness opened by rifting, for example where Ferrigno ice stream is shown, ice flow and erosion of the rock beneath it becomes particularly concentrated. As a result, when ice was at its maximum, a lot of ice drained from central West Antarctica along the rift beneath Ferrigno ice stream, and this intensified ice flow further out over what is now the continental shelf, so that when ice retreated again, a deep trough was left in place in front of the ice sheet margin. You're now looking at today's situation, where that trough, represented in green, and which is currently under the sea, is located in front of Ferrigno ice stream, which is overlying the rift further inland. In the current era, sea level is such that it now covers the continental shelf and that trough in front of the margin. I've just made that sea transparent there again, so you still have an impression of where the offshore troughs exist, such as the one in front of Ferrigno ice stream. Now, what recent research seems to be demonstrating is that today, submarine troughs such as this offer paths for relatively warm ocean water to reach the current ice margin and encourage melting, and hence ice thinning along parts of the Antarctic coastline, particularly here in West Antarctica. I've brought back into the visualization there the drape of ice thinning to highlight the correspondence between the offshore troughs in green and the coastal areas of ice thinning in red. So finally, removing all the ice cover and simply looking at the shape of the land today, you can see clearly beneath Ferrigno ice stream in green the deep rift in the topography which in the past directed ice flow out into the trough in the foreground. We argue that it's this trough in turn that now routes warm ocean water back towards the current ice margin, and that the thinning further inland through Ferrigno ice stream is steered back inland directly along the path initially opened by the continental rifting. In conclusion, the ice thinning we see today is not only a short-term response to the climate warming, but it also forms part of a wider, sustained, and complex series of interactions between geological activity, glacial landscape modification, and oceanic and atmospheric changes that have occurred over millions of years.